Okay, so we have hydronium ion reacting with the hydroxide ion to form water and water. Remember that. Now, what we just proved in the previous video is that the hydronium ion never actually runs out. How could that be? If only we knew of some kind of theory out there that would suggest that there's always going to be some of that reactant always present. Oh, wait, maybe we do. Maybe we could apply the idea of equilibrium to help us. Oh, yes, we can. If I change this guy to a reversible reaction, that will explain everything. What that would suggest is that no matter how much hydronium or how much hydroxide ions we put in there to cancel each other out, we're going to be pushing a bunch of water. Like if in this case we had hydronium ions to start with and we increased the amount of hydroxides in solution, which shifted the equilibrium to the right to form more and more and more and more and more water. Oh yeah, we're getting more and more and more. But wait a minute. If water is going to be formed, the only way that we can suggest why the hydronium does not run out is because there's always a little bit of that reverse reaction happening, which provides us with some hydronium ions in solution. Is it a lot? Absolutely not. So when we talk about the equilibrium constant, we're going to know that this is going to be a very, very big number. However, they don't typically like to have water in the denominator. And so what they typically do is instead of writing it like this, they write it like this. They write the water first, and then the hydronium and hydroxide ion over there. And so this is how they do it. Now, we can write our KEQ for this. And for this KEQ, or equilibrium constant, we would expect this number to be very, very small. So when we write our equilibrium constant, we are going to write KEQ is equal to the concentration of the products, which would be concentration of the hydronium ion times the concentration of the hydroxide ion, like that. And then we would divide that by the products. However, we do not write water in equilibrium expression constants because you can't talk about the concentration of water. It doesn't make any sense because water is part of the solution. You can't talk about the concentration of water. It doesn't make any sense. So therefore, this is our equilibrium constant. So we actually know what the equilibrium value is. There has been tons of studies done in this that have allowed us to be able to determine, and we know what the equilibrium constant is for water. And when we talk about water like this reaction is profound. If you take a cup of water at your house, it's undergoing a reversible reaction right now. It is taking those water molecules. One of them is taking a hydrogen from the other, and it's forming hydronium, and then it's also forming hydroxide ion. Now, is there a lot of those in your solution? Absolutely not. It's not. And why can water be both an acid and a base? Well, because it can form both hydronium and hydroxide ions. So this is what's known as the auto-ionization of water. Water itself will ionize. Will it ionize a bunch? No, it will not. There's very, very little conductivity of just pure water, which would suggest that you are forming only a little bit of hydronium and hydroxide ions, but you still have some, but not very much. But for the ionization of water, they call this Kw. That's what the equilibrium constant is called for water, and it is equal to a value of 1 times 10 to the negative 14, like that. It's a very, very small number, suggesting that water is the primary thing that's present.